Good day to each of you. This presentation is called the Modern Day Space Elevator 101, as it reflects the 20 years of remarkable engineering designs and a discovery of a material that will enable space elevators during the next decade. The concept discussed here will transform how we think about how we're going to reach our destinations in space. We will work with rockets in a cooperation and competitive manner, leveraging the strengths of both. This dual space access strategy is a major thrust in the modern day space elevator. We will talk about visions, transformational strengths, then why space elevators, and finally, bring you up to speed on the development programs. I will run through this rapidly, but the videos and charts will be on our website and YouTube's. Okay, well, let's get going. We're going to be talking about this process, the concept of dual space access, because we know that rockets have tremendous strengths and space elevators will transform the other aspects of how we get to space. The concept of a space elevator is relatively simple. It's a long tether, 100,000 kilometers long, anchored at the equator in the middle of the Pacific, rotating with the Earth such that you have force outward, centrifugal, I always have trouble saying that, force outward that keeps the tether straight. It's like circling around your body in a rapid manner with a string with a rock on the end of it. I like the lower right-hand chart because it shows the magnitude. The tether would reach beyond the bow shock of the Earth's magnetic field. Okay, one of the things we want to assess in this is where are we going for humanity's sake? We want to definitely improve the conditions on the Earth. We do that a lot. In addition, we want to enable going out there. So what are our visions that we're looking at today? Well, we've got the NASA vision. We are putting people on the moon again. We have China and Russia doing the same thing. The NASA program has 26 partners, as I believe they are now. I don't know if they've signed anybody lately. We're going to have a place on the moon. We're going to have a place on Mars. We've got different players, and we've got the concept a little bit more future of having rotating cylinders in space, like at the altitude of the moon, with 1 million people. So we have big visions. And here's the National Space Society vision. It took me 6 months to find out how much mass they had planned on using. It was a difficult thing because nobody ever asked the question, how much mass? 10,500,000 tons delivered to the altitude of the moon. Think about that a little bit. Okay, so the next one is we are in reality today. Whoops. We are in reality. There is a contract to move 8 or 9 people around the moon with a starship in the near future. Just mentioning some visions here. Here's the idea that NASA has signed a contract with SpaceX for delivery to the surface of the moon. We have also Mr. Musk's idea of going to Mars. We're going to have SpaceX delivery of vehicles for people to go there in the next 10 years. Okay, but nobody ever asked how much does it weigh? And when we're talking about going to space, we have to use the rocket equation or space elevators. But if we look at our visions today, space solar power, let's provide 12% of the global electrical need for the future. That's 3 million tons to GEO. The moon village is 500,000 tons to the surface of the moon. Oh, and then let's talk about SpaceX colony on the moon. On Mars. He says 1 million tons to the surface of Mars. With rockets, that's kind of hard. Then there's the planetary sun shields to cool the Earth. Many different programs, and they all weigh a lot. So we have a vision on space elevators for the 2038 timeframe. Space elevators are the green road to space while we enable humanity's most important missions by moving massive tonnage to GEO and beyond. We're green because we don't burn anything in the atmosphere, etc. We're green because we don't leave any assets in low Earth orbit or in the debris zones. We just lift things from the surface of the ocean in a nice, slow tether climber to get up to geo in about a week. The approach is simple. It's like a bridge. We're going to be a permanent transportation infrastructure, like a bridge going across a big river. Okay, the vision of the galactic harbors. The kicker is, as we increase the number of space elevators, we'll start with one, and then we'll put one up right next to it and call that a galactic harbor. It's for up and down, or two up, or whatever. And that's the way the commercial world will probably develop it. So the plan is to have 7 climbers per week per elevator. And that would be 30,000 tons per year. Well, what we're addressing with the space elevators is the conundrum of rockets. They lift off the planet and then they throw away a lot of stuff. Now, even if you reuse it, it turns out the rocket equation doesn't change. Roughly 2% of the rocket pad mass gets to geosynchronous, and 0.5% gets to the surface of the moon. I'm showing that chart here. It's a NASA launch called Apollo. It goes to the moon, but it leaves its parts all the way along the way. The current planning for NASA is the same. They're going to deliver less than 0.5% of the pad on the mass to the surface of the moon. That's the rocket equation. So what are space elevators' transformational strengths I've been talking about? Well, let's talk about them. We have the modern day space elevator basic concepts that we're working with today that are going to transform space access. The first is we're ready to enter the engineering development phase, phase 2. We're going to get into that later in the development side. We are the green road to space, so we're going to transition the road up there to much more environmentally friendly. We want to join the advanced rockets, and we have tremendous strengths because we're a permanent infrastructure. So the transformational characteristics will revolutionize the future. Here's the transformational characteristics we're talking about. Daily, routine, safely, inexpensive. Think bridge, permanent space infrastructure. Unmatched efficiencies. We deliver 70% to geosynchronous and the lunar orbit, whereas the rockets deliver 2% to basically geo and like 1% to the orbit around the moon. We do massive movement, unmatched today. Green road to space. We have unmatched velocity. When we leave at the top of the apex anchor at the top of the tether, we're going 7.76 kilometers per second. We get to the moon in 14 hours. We get to Mars in 61 days. Well, we wouldn't have any rocket fairing issues. You know, it's a little slow train going north. We'd have assembly at the top of the gravity well. I'm going to talk about this a little bit later, but think about building a huge spacecraft above the gravity well. And then the economics are remarkable. Strength 1, daily. We're like a bridge, daily, routine, inexpensive, reliable, safe, et cetera, et cetera, et cetera. So we had students at the Arizona State University doing some studies for us. And we asked them to do a bus schedule to Mars. Concept is remarkable. Can you imagine a bus schedule for going to Mars? I mean, rockets, every 26 months, they get to send a flotilla. But we're talking about everyday release. Now, some trips are fast, 61 days. Some are 400 days, but you send your hammer and nails on the 400 days and you send your pizza on the 61 days. This is a characteristic set for bridges and space elevators. Efficient, commercial, low cost, permanent, safe, et cetera, et cetera. It's a bridge. That's all it is, a bridge to space. So we have an unmatched efficiency. Now, we talked about Apollo, 0.5% to the surface of the moon. Well, we can send 70% to the lunar orbit, and then we'd use some fuel and stuff to land on the surface of the moon, of course. So it wouldn't quite be 70%. It'd be a heck of a lot better than 0.5%. So the unmatched efficiency by itself justifies space elevators. Oh, by the way, we do it fast. We can get to Mars in 61 days. By the way, that's without any fuel. That's just a release from the top of the space elevator. And by the way, we do it every day. We don't have to wait 26 months. So we have unmatched liftoff capacity in a year, 30,000 tons for a group of space elevators going to Mars each year. And then we get back to this conundrum of rockets where they just have trouble delivering anything more than 0.5% or 1% to any place out there like geosynchronous orbit and beyond. Whereas the space elevators are in the 70% region. Here's a little chart I like. I tried to summarize what we'd done in our past. It took me about 6 months to figure this out, and I'm not sure I'm anywhere close. But 22,000 tons to orbit, mostly low Earth orbit, between 57 and 20. We're hoping to do 30,000 in the first year of operations. Okay, the Green Road to Space, remarkable concept. It really is. It's a capability to share the necessary transport to geo and beyond with rockets. Now, rockets do really great movement through radiation belts rapidly, so people should use rockets. They do a very good job at low Earth orbits. So those two strengths we want to leverage for the whole concept of access to space. But if you're going any place, geo and beyond, space elevators are designed for that. Okay, here's a basic concept of how it works. We're rotating around with a long arm. So at the end, you're really going fast. Turns out it's 100,000 kilometers, which is the standard design right now for a space elevator. You go to Mars without any fuel. You go past Mars with enough energy. Now, you'd have to have a little rocket engine on the package so you can slow down rendezvous or land on Mars. But if we extend it all the way to what I call the scientific version, which gives you 12.35 kilometers per second, you can leave the solar system. But even more important, you can go to any planet inside our solar system very rapidly. Then we have the sixth strength, which is reduce the requirements for the rocket fairing. The James Webb telescope had to really squeeze to fit in the top of the rocket. And then it had to survive the rock and roll of a rocket launch. We have open boxes that we can use for tethered climbers, and there is no rock and roll. The assembly at the top of the gravity well. Think about assembling a USS Star Trek vehicle up there. Can you imagine putting a huge spacecraft up there? Well, I can, because what we do is we take 14 tons per day, raise it up to the top, and assemble it into any massive satellite you want. So we can go to any planet in our solar system with a huge spacecraft at high speed. Think 200 days to Neptune. Now we have enough rocket assembled to have a big engine on it so you can turn around and slow down like a nuclear engine on it. Then what we do is we turn around and we investigate Neptune for a while and then use the nuclear and planetary assist and come home, maybe a 10-year mission. Okay, strength 8, the transformation of the economics. Now, I'm not really into this as an engineer, but let me point out that if you have a permanent infrastructure and you open it up to commercial investors, they will put McDonald's and hotels and refueling stations and assembly plants and all that kind of stuff along the space elevator. So what it does is it opens up business opportunities along the 100,000 kilometer line. Okay, now we're going to talk about why space elevators. Essentially, it's the same as what I've been mentioning before, but let's make sure we've got it down. The transforming of the economics. I'm sorry, I just went backwards here on that one. We don't want to do that. Okay, there we go. Now we got why space elevators? Basically, because we must. Okay, there's a lot of people dreaming for a lot of activities off planet. And if you can do 30,000 tons per year, you can talk about visions on Mars and the moon and Lagrange point 5. Because if we're working with rockets, we can move people and move massive equipment to the destinations of choice. So what we need to do is we have an elegant answer for space elevator's question, which is why. The answer is we have unmatched efficiency. We can throw stuff out there at huge rates that can be caught at the other end. We have unmatched velocities, huge velocities. We have unmatched movement of logistics mass, 30,000 tons in the first year and grows from there. And we have to mention that we're the green road to space. So we have many planners out there putting roads to space, but we have the green road that's highly efficient. So advanced rockets will definitely open up the moon and Mars because they're now here, and they'll be doing it in the next 10 to 12 to 15 years. When the space elevator becomes operational in like 2038, we'll be joining the advanced rockets in supplying the logistics needed for developing locations around the solar system. So we really want to work with advanced rockets in a dual space access architecture strategy. So where are we in development? Okay, the first thing is we want to do it in stages. One's first space elevator, then you do the second, and now you have a galactic harbor, and the competition will drive 2 more galactic harbors at least. Here's a body of knowledge residing at the International Space Elevator Consortium's website. We've got 14 18-month studies that were done that have covered most of the technologies we've been talking about. There are 2 International Academy of Astronautics studies that are out there that result in the answer that space elevators are feasible. One in 2014 and one in 2019. And the answer is they've looked at all the different technologies and come to answers that lead to they're feasible. Now, this is what it looks like when you lay out a plan for development of a major system. And we're past the assessment of the technology. We're now entering how do we validate the engineering? Well, there's a simple word for that. It's called testing. So we're at that point where we're starting to move into test planning and then set up test environments and then test the different components of the space elevator. Here's a good look at a schedule. I'll pick any schedule you want. We're looking at like 38 being operational, somewhere right around in there. There's a better look at what we're planning. The tether goes to 100,000 kilometers up, but there are so many advantages along the way. The one that's obvious, a geosynchronous node. If we bring logistic support to whoever is working at geo, then we just offload it there and it floats next to the tether for a while until somebody comes and picks it up with a tugboat, moves it to where they want to do it. But we can have refueling, reassembly, we can have growing mass into different satellites. We can do all kinds of construction up there. And then you go further, you can go to the moon and Mars, or you can go all the way up to the apex sector, get the full velocity, and get to the moon in 14 hours and Mars in 61 days. The concept is simple. We have 3 regions that are really productive for us. The Earth port, obviously, you've got to translate a transportation load from the sea or air and turn it vertical and put it on the tether climber and take it to geo, where we have tremendous customer base that will supply with a lot of assembly and refueling and all that kind of stuff. And then we keep going up to the apex sector where I've talked about you have tremendous energy and you can go to any place in the solar system. The concept is simple. 3 galactic harbors, and we can provide payloads going to any planet in the solar system. The vision is really that we're going to support rockets as they move people to the moon and Mars. And we're going to supply all the logistics, on-time delivery of logistics. How does it become real? Well, we start with a reel of tether and take it to geo, extend it down, extend it up. The center of mass stays at geo. And then you let more string down and more string up and keep going until you grab it at the ocean. And then you let the apex anchor go a little bit further out so the force in the tether is outward. And then you have small tethered climbers that actually build the tether. They bring along tether and they, just attach it to the current tether to build up the strength. You do that for a lot. I've heard numbers like 275 trips, something like that. Anyway, so now you put all those tether climbers up at the apex anchor to provide more force up there. And now you have an operational space elevator. Here's what Earthport would look like. Just think of a train station. Okay, it comes in from one location, it goes to another. That's all it is. Here are some early designs: a tether climber with tether to build up the tether. We have, apex anchor on the left. That's a heavy dude that takes the whole reel of space up and then goes to the top. We have a tethered climber. This is a baseline tethered climber. There are all kinds of other ideas. People have different concepts. Then we have to look at the material. Well, the material that surfaced in the last 8 to 10 years is single crystal graphene. Now, there are about 30 or 40 other two-dimensional materials that have similar characteristics to single crystal graphene. It's just that single crystal graphene is leading the pack right now in development. And they have come out with a single sheet of single crystal graphene in many locations. What does that mean? Well, single crystal graphene is 1 atom thick. And then you can make it 1 meter wide and 100,000 kilometers long. So that would be one strand of your tether. Now, the current estimate is like 12,000 of those layers put together into one graphene tether. But let me tell you, we're early in that. But the concept is there and it is feasible. People have been talking about it. And yes, graphene tether material is possible. Okay, this is what I look at and I really like it. It's a green road to space. There's the concept. We've got a long way to go, folks. I'm not saying it's there today, but it's almost there. And if you look at the different materials that can be used for a tether, the 20th century stuff doesn't cut it. So we have to go to the 21st century, which is carbon nanotubes and boron nitride tubes. But then we came up with the graphene, the two-dimensional material, and that's leading the way right now. And it's really looking like it's 140, 150 gigapascal type capability in those in the graphene they're producing. Graphene is strong enough in a candidate tether. It should be able to be produced in a linear manner to be long enough. This is the way it would be done. It would be in a place where you'd put in a material, a gaseous material, and the carbon atoms would then bond at the bottom on the liquid metal, and then you'd pull it out of the furnace and end up with a reel. Well, this is a little calculation. We're talking about a single piece of single crystal graphene, and it would be 77 kilograms when it's 100,000 kilometers long. So it's very, very light. Just some pictures of current locations, developing the concepts on how we would do it and what it is. We're not there yet. These are just images of production concepts. So the elegant answer to why we need space elevators is relatively straightforward. We're permanent transportation infrastructure that acts like a bridge to space. Some of the characteristics is we have unmatched efficiency, 70%. Unmatched velocity, nobody can match that. Unmatched movement of logistics mass. We are logistics king. We will be providing logistics with on-time delivery. And then, of course, we have the tremendous advantage that we're the green road to space, and we will help our environment from 2 or 3 different ways. So why space elevators? The answer is simple: we must. We need to fulfill the dreams that I started with. There are so many dreams. We must fulfill them. And about the only way to do it is to have a simple answer called an elegant solution to the rocket equation, which is space elevators. Anyway, thank you very much. And this is the modern day space elevator 101 concept. If you have any questions, go to our website, www.isic.org. Thank you very much.